A capacitor consists of two parallel plates separated by a distance d. We define the capacitance of a capacitor by the ratio of the charge Q that the plates can hold divided by the potential difference across those plates. Capacitance has the letter big C, and we have this formula for it, C equals Q over delta V. It's worth noting that capacitance is dependent upon the physical geometry of the plates. Consider the charged parallel plates shown on the right. Assume that the plates are not in contact with anything, so the charge on them remains constant. We've seen in the past that electric field between two oppositely charged parallel capacitor plates will be given by E equals sigma over epsilon naught. We used Gauss's law to derive this equation. We also have a potential difference formula, delta V equals E delta X, which could be useful in this situation as well. We want to compare the electric potential difference in these situations and see which setup has the higher delta V, or would they actually be equal? In this situation, we see that the number of charges on the right and left is the same. So I'm going to say that we've got positive Q on this plate and negative Q on the other plate. That's actually going to be really common for capacitors in practice. When one plate has a certain amount of charge on it, it'll attract an equal and opposite amount of charge on the other plate. And so since the conductors are not in contact with anything, the amount of charge remains the same, even if the distance between them changes. If we use the formula for electric field, we can see that the field is not dependent upon the separation between the plates. So we're actually going to have an equal amount of field in both cases. The number of field lines shows us how strong the field is. So we actually just want an equal number of field lines in both cases. If there's a field E in setup A, then there will be an equal field of E in setup B. Now we want to use the formula delta V equals E delta X to decide what the potential difference is like for these plates. In case A, we'll have delta V equals E times D, where D represents the separation between the plates. Down here, though, we'll have delta V equals E times 2D. 2D represents the new separation between the plates. Delta V for setup A is E times D, but delta V for setup B is 2 times E times D. A battery is a device which can provide a constant potential difference between two terminals. The terminals are metal conductors, as seen in the picture. The terminals are going to be insulated such that current can't flow directly from the positive to the negative. If it was allowed to flow through a conducting wire, we would have what would be known as a short circuit. We don't want that. Now, if the battery is the only element in consideration, we're typically going to label the negative terminal as being at 0 volts, and the positive terminal will have some positive voltage depending on the potential difference that the battery supplies. In the case of a simple handheld D cell, the potential difference is going to be 1.5 volts. So we label the negative terminal 0 volts and the positive terminal plus 1.5 volts. Let's see what happens if we connect the battery terminals directly to capacitor plates. A capacitor is a device that can store electric charge. Each plate of the capacitor can be connected to a different terminal of the battery. If the capacitor is initially uncharged, the battery will cause charges to flow onto the plates. It will push the charges onto the plates. The charge carriers also want to reach the other side, but most cannot jump across the gap, unless some kind of dielectric breakdown of the medium between the plates occurs, such as a spark of some kind. Consider the charged parallel plates at the right. They're connected to the battery terminals through conducting wires. We'd like to analyze this situation comparing the electric field and comparing the charge on the plates. Now, first of all, one thing we know about conductors is when they are in electrostatic equilibrium and two surfaces are in contact, then the potential of one point on the conductor is going to be the same as the potential on another part of the conductor. If those potentials didn't match, then the charges would shift themselves so that they do match, as long as we're talking about electrostatic equilibrium. So if this point on our terminal is 0 volts, then this point on our plate is also 0 volts. Looking at setup B, the same thing would occur. Points which are in contact will have the same potential. So if there's plus 1.5 volts on this terminal, there must also be plus 1.5 volts on the plate that it's in contact with. So this is different from what we had above. Above, we said that if the plates were moved farther apart, the delta V would change. And let's just say, for the sake of argument, that this was a 0 volt potential and this was a 1.5 volt potential. Then when we move the plates apart, the separation would now be twice as much. So this would become a 3 volt potential. Okay, but that's because the plates weren't in contact with a battery, which defined what the potentials on them was. Here, because we are in contact with the battery, whatever delta V we have for setup A is going to be the same as the delta V we'll have for setup B. In this case, it's 1.5 volts. All right, so we have the formula delta V equals E delta X. Delta V is going to remain constant for this situation. So as delta X goes up, we expect our electric field to go down. We can rearrange this formula to solve for E. And let's just do it for each setup. So for setup A, we'll have E equals 1.5 volts over 0.02 meters. 75 newtons per coulomb. Okay. For setup B, we have the same potential difference, larger spacing, 37.5 newtons per coulomb. All right, so we want to show that the field is stronger in A than in B. And one way to do that is to just draw a proportionally larger number of field lines. What this example illustrates is that when our capacitor plates are moved closer together, the field becomes stronger. So the geometry of the capacitor plays a part in how strong the field will be. But another thing to analyze is the amount of charge on each capacitor. And how could we find out the amount of charge? Well, we have the formula E equals sigma over epsilon naught. But if we remember the definition of sigma, it's Q over A. So we would have this. Now we know that the surface area of each plate is going to stay constant in both setups. It's 0.1 meters squared for both. So this remains constant. The epsilon naught remains constant because that's just the permittivity of free space. So with this in mind, when our electric field goes down, what happens to the charge on the plates? It goes down as well. And we can actually calculate what the charge on each plate is. So let's do the calculation for setup A, and then we'll do it for setup B. If I rearrange the formula, I get Q equals E times A times epsilon naught. So for A, it would be 75 volts per meter times the surface area of a plate times our epsilon naught. All right, so I got 6.64 times 10 to the minus 11 coulombs for setup A. And now we just want to find the charge on setup B. So we have to use B's field and the area and epsilon naught. It's going to be 3.32 times 10 to the minus 11 coulombs. So half as much charge. Now, one of the ways we can indicate that there's more charge on setup A is we can just have more pluses. That's one way to let a viewer know that this object is more charged. And this tells us something profound about connecting a capacitor to a source of constant potential difference, such as a battery. What the battery can do is it can actually push charges onto the capacitor or remove charge from it, depending on the geometry of that capacitor. So as the plates get moved closer together, the battery pushes more charge onto the plates. And the charges on the plates are attracted to the other side. When the plates are removed from each other, the charge starts to come off the plates, and it can go into the battery. Now let's calculate the capacitance of each of these capacitors. We have several formulas describing this situation. And one of our formulas for capacitance is that it's a rate of charge to potential difference. But using all these formulas from the past, we can arrive at a new formula which determines our capacitance based on the geometry of the capacitor. Let's start with the original formula, C equals Q over delta V, and we want to derive this new formula. So one thing to substitute in is that delta V can be thought of as a field times a distance between the plates. And when it comes to charge, if we multiply that A to the other side, we can substitute in the expression sigma times A for that. Now, using this formula here, we see that the field can be expressed as sigma over epsilon naught. And then by flipping that fraction, we'll get this. Finally, we'll cancel off the surface charges to reveal that the charge that's on the plates doesn't alone determine the capacitance. Instead, the capacitance can be given by A epsilon naught over D. All right, let's calculate these capacitances. The capacitance of setup A is 4.4 times 10 to the minus 11 farads. Big F, farad, is going to be the unit of capacitance. A farad is defined as a coulomb per volt. Now let's calculate the capacitance of setup B. Same area. Larger separation. This cuts the capacitance in half. So even though they're made of the same materials, the capacitance of A is twice as much as the capacitance of B. And what does this mean when it comes to their ability to hold charge? Well, we said that A would have a very strong field. And A would be able to hold a lot more charge, given the same delta V, compared to setup B, with a weak field and less charge. Now, just for the sake of confirming what we had said, let's calculate the capacitances the other way as well. All right, we had said earlier that the charge on A was 6.64 times 10 to the minus 11 coulombs. And we said that the charge on B was 3.32 times 10 to the minus 11 coulombs. So now I'd like to use the other formula for capacitance, and let's see if it holds. We have to divide the charge on the plates by the potential difference across the plates. And we again get 4.4 times 10 to the minus 11 farads. If we do it for setup B, we get half the capacitance as expected. So this just shows two ways of calculating the capacitance of a capacitor. You can do it from the geometry of the plates. That would be the area and the distance between them. Or you can do it based on the charge that they're holding, dividing by the potential difference across them.